Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to have Ilya Blum-Rosen here. He is a postdoc candidate and very interested in what he's going to be talking about. He's going to be talking about communication effects in economic environments.
Thank you, Jennifer. Thank you very much for having me here. I'm very happy to be here in Microsoft. So the title of my talk is Communication Effects in Economic Environments. And actually, in every protocol or every game, the participants are communicating in some pattern. And it turns out that from just looking at this communication pattern, we can say several things about the power and the limitations of these protocols. So in this talk, I'll try to survey some results from this line of research that tries to analyze the communication patterns in game-theoretic environments. And I'll start with a short background on the relationship between computer science and economics, because for those who don't know anything about the relationship, it might be surprising to hear. And then I'll discuss two examples for such communication patterns in game-theoretic environments. I'll start with a discussion about severe restrictions on the communication lines in a mechanism design framework. And I'll start with the auction in a simple auction framework, and then I'll generalize it to a mechanism design setting. And then I will talk about the most common mean of communication in economic environments, which are prices. And I will focus on prices that are ascending in time, like in eBay, for example. So in recent years, we've witnessed the interesting phenomena that computer science is gradually expanding towards other disciplines. We can see a nice work going on in computational biology, or in quantum computation, or in computational economics. This is the topic of today's talk, or algorithmic game theory. And it turns out that computer science is now providing some toolbox of concepts and instruments to other disciplines, the way that mathematics used to do in the past. So, but when we try to analyze jointly these different disciplines, we encounter some obstacles. For example, if we compare the classic computer science theory and the classic economics, we can see that they differ in several properties. For example, the classic computer science is constructive or normative. We want to design a certain computer. We want to design an algorithm or a protocol. We want to know how to do it. While the traditional economics is more descriptive. The economist observes some phenomena and try to explain them by modeling it in a mathematical model. The classic computer science is more centralized. We design the algorithm. We tell each participant how he should behave, what computations he should do, what messages he should transfer. While the economic environments, in the economic environments, the participants have selfish behavior. Okay, the different computers in the network are maybe owned by different companies, by private companies. Okay, so, and they may manipulate the protocol if it is beneficial for them. And another example is that classic computer science theory mainly deals with the worst case analysis, while in economics it is more popular to assume prior distribution on the state of the world and analyze the the world from an average case point of view. So in the last few years, we've witnessed, mainly due to the emergence of the internet, we've noticed some new environments that combines properties from these two disciplines. I would call these environments electronic markets, but it's just an example. And for example, in these electronic markets, we should do a constructive research. We want to know how to design these new environments, or we want to know how to create new protocols for these electronic markets. But the participants in these markets are selfish. They will manipulate us if they can. And it is not clear if the research should be done in worst case or in average case. And we also have new properties in these electronic markets. For example, the changes in these new environments are very rapid. For example, if you have a new file sharing system, then it may be the leading system in a very short time, what took decades for older environments. So when we want to analyze these new environments, we have to take into account concepts and notions from both disciplines. For example, from economics, we may want to analyze the way that the players will behave. We want to analyze these new markets in an equilibrium state. Or we will probably use prices for this matter. We also may give incentives for the players to join the game, to participate in the game. And we also have to take into account that the information that is available for the players is non-symmetric. Different players have different information. From the computer science side, we have to make sure that our mechanisms are feasible. That, for example, if you want to find some solution to this game or to the market, then we should find it in a polynomial time, for example. And if we cannot find it in polynomial time, maybe we want to approximate the solution. And we don't always want to, for example, maximize the seller revenue as traditionally is done in economics. We may have different objectives. For example, we may want to minimize the make span in the system. So we see that we have to use different tools for these new environments. And some examples for these environments are the business-to-business trade that is done on the web, the stock markets that are now, all of them are computerized, P2P systems in which incentives play a very important role. And when we try to think about what will be the how will e-commerce look like in 10 or 20 years from now? This is a difficult question. Can we know how people will trade in 10 or 20 years from now? Can we know what actions that are currently done by humans will be done by computers like 10 years from now? So the main question is, can we design these future environments using the tools that we have today, either from computer science or economics? And it seems that we need some new theory, some unified theory of these two disciplines. And for using this theory and for developing this theory, the researchers must have deep knowledge in both areas, in both computer science and economics. So in this talk, I will demonstrate these ideas on this issue of analyzing the communication patterns in game-theoretic environments. So what are communication patterns? Communication patterns in economic environments are maybe very simple. For example, if I raise my hand, this is a binary communication pattern. For example, I can raise my hand and say that I want to buy this item at this price, or that I don't want to buy it at this price. So this is a first example. Another example may be sequential protocol. I must send a message, and then you respond, and then the third player should send his message, and I should send a message again. So this is also a communication pattern. And as mentioned, the prices are maybe the oldest communication pattern in these game-theoretic or economic environments. And for example, if we are forced the prices to be ascending over time, this is some restriction on the communication. So we see that we can classify the different protocols, the different economic environments, according to the communication pattern that is used in these that are used in these environments. So, given some communication pattern, we would like to know what is the optimal thing that we can do under this the restriction to a certain pattern, and how much loss is incurred comparing to the state when we are not restricted to use any communication pattern. And then we can add up some constraint from economics, for example, that we want the players to behave in an equilibrium, or we may add computational restrictions, for example, that the computation will be done in polynomial time. So these are the main questions that we will ask. And in this talk, I will serve with some results from this paper, which are joint work with Noam Nisan, Ilya Segal, and Michal Feldman. Okay, so I'll start. In the first part of my talk, I will talk about settings with severely bounded communication, that the communication between the participants and the organizer or the auctioneer in the case of auctions are very limited. So I'll start by introducing that concept of auction. In an auction, we have one item for sale in a single item auction. And an auction is actually an algorithm. The input for the algorithm are the actions or the bids of the players. And the output of the algorithm is the identity of the winner. The identity of the winner, the payment that the players are paying. Okay. For example, I have to switch the gadget. If we have two players, one of them is willing to pay $80 for some item, and the second one is willing to pay $40 for the item, then these players should choose some bid or some action, and then the auctioneer observes these actions and should decide who gets the item. And the goal in this talk will be to maximize the social welfare or the social happiness. Or in other words, we want to allocate the item to the player that wants it the most. For example, here, this player would be willing to pay more for the item than this player, so the society will prefer that this player will get the item. Okay, so
why do you call it social welfare and not the power of the rich? Because maybe I really value it more, but Bill Gates has more money, so he just puts down more money.
No, but if he's willing to pay more money, then he needs it more. Okay, so this is the assumption here.
So richer people have bigger needs.
Yeah. This is a standard economic measure. So our goal here is to indeed allocate the item to the player with the highest value, but we want more. We have a further restriction. We want to have an equilibrium. We want the players to act according to a dominant strategy. So what is a dominant strategy? Some strategy for the player will be dominant if it's the optimal thing to do, regardless of the actions of the other people. We will see an example later on. So allocating the item to the player that wants it the most is actually solved from the economic point of view. If we use the victory auctions or the second price auction, we do just that. We give the item to the player that wanted the most, and we have dominant strategy equilibrium. So what is the trick? We have to allocate the item to the player with the highest bid, but this player will pay the second highest bid. This ensures us that all the players will tell us the truth. They will tell us the true value. And so the auctioneer will have the true data, and he can choose the player with the highest value. Okay? So from the economic problem, this standard problem of single item auction is solved. So let's see an example. Assume that the two player has some value that is distributed uniformly in the range 0, 1. So the optimal welfare, the optimal expected welfare, will be the expected value of the maximal value among these two values, and it is easy to see that it equals 2/3. Okay. This is just an example. Okay, so, but what is the problem? Recall that we said that the players can actually directly reveal their true data to the auctioneer. They have what is called in economics a direct revelation mechanism. They can just simply report their private type, or in other words, the standard economic models assume that there is an isomorphism between the type space of the players and the action space or the bid space that they can use. Okay? But in many reasonable environments, there is no isomorphism between the type space and the action space, but the players can only choose an action from a small number of discrete actions. Okay? So in this part of the talk, I will talk about situations where this action space is severely bounded. So there will be some inherent information constraint that where the auctioneer will not be able to always know who has the highest value. Yes?
You said it happened in many realistic scenarios. Can you give some? Because Teletab is not
yeah, I think my son will not agree with this observation. But in the next slide, I'll give some motivation for this. Okay. So as I said, in this work, we'll try to see what happens if the action space is severely bounded. So we have an information theoretic problem for the auctioneer to know, for example, in this example, who has the highest value. Okay. So we can see that in many settings, we have players with a continuum of types, but only a small number of k possible actions. So what may be the reason for these restrictions on the action space? Well, first, the restriction may be caused by behavioral or regulatory reasons. For example, in many cases, the auctioneer or the seller don't want to have like a bid process or a negotiation process. He just wants to decide on a price and give a take it or leave it offer. This is the price. Are you willing to buy or not? So the action of the player is just either to buy the item or not to buy the item. So he has only two actions, despite the fact that he may have a continuum of different types. Another example is, for example, in insurance policies. Assume that we are an insurance company and we want to sell insurance policies for drivers. And drivers may have a continuum of different risk levels, or each one has a privately known probability to make an accident. So in principle, we may want to design a special insurance policy for every driver, but it's not the case in real world. In real world, we have some packages, some insurance packages that the insurance company may sell, and it is a small number, like 3 or 4, and it also holds for example, for cellular phone companies that also advertise small number of packages, although the types of the players are maybe much larger. Another constraint may be technical. For example, if you want to sell in a standard English auction, like in eBay, we want to sell some item, then we may not want to use some very small epsilon increments in the auction, but rather we may want to use like $100 or $1,000 increments in order that the auction will terminate very quickly. Another example is physical communication constraints. For example, if we want to auction something on a network, we may not want to use more than a couple of bits for this purpose, so we may have strict communication problems. And the last thing is that players traditionally are not willing to reveal their private data. They are more willing to answer questions like take it or leave it offer, but they think that maybe tomorrow will be another game or another transaction, so they are not willing to give their private data, but just they will be willing to answer different sort of questions. So this is a short motivation for this work. And now I'll like to discuss a simple case, the simple auction case, and I will demonstrate the main questions and main solutions for this problem using this very simple auction model, and then I will generalize this result in few generalization levels. So let's start with 2 players, where the type of each player, the amount of money that he is willing to pay for the item, is uniformly distributed between 0 and 1. But the main assumption here is that each player has only 2 actions to choose for. We denote them by 0 and 1. Actually, it means that each player can only send 1 bit to the mechanism instead of an infinite number of bits in standard auctions, because in the traditional economic literature, each player may send a real number to the auctioneer. So the valuations are uniformly distributed independently in 0, 1, and each bidder would like to maximize his own utility, which is his value minus the payment that he pays to the mechanism. So let's see an example for such a mechanism. In this example, in each entry, we write who wins the item. For example, if both players choose the action 0, then Bob wins the item. If Alice chooses action 1 and Bob chooses the action 0, then Alice wins. Okay? But we also need to define some strategies for the player. What is a strategy for a player in this model? Recall that each player has a continuum of types, but only 2 actions. So he must have some way to translate his own private data to an action. So this is a function from the range 0, 1, the type space, to the action space, to the set of actions 0, 1. So let's take a look at this example. Here, the strategy of Alice is the following strategy. Alice will choose the action 0 when her value is smaller than 1/3, and she will choose the action 1 otherwise. We call this strategy a threshold strategy. And Bob will also use a threshold strategy with a threshold 2/3. Okay. So this is an example for a 2-action auction. And now, I claim that this mechanism is the best thing we can do. This is the best solution for the information theoretic problem, okay, that we force the agent only to use 2 actions. Okay.
What do you pay?
I will, this is the empty spots here. I will write the payment right away, but here I only want to discuss the allocation, the best allocation. We want to maximize the expected welfare in the system, so just here I only want to talk about the welfare without the payments. Okay. The definition of the expected welfare does not take into account the issue of payments. So interestingly, this optimum mechanism achieves an expected welfare of 2/3 minus 1/54. And recall that we saw that in the case with it, we don't have any restrictions.
Can you, I'm sorry, I don't see how that, I can't do that in my head. Can you point out to us where those are?
Why this is the expected welfare is this welfare?
Yeah.
Alice will choose the action 0 with probability of 1/3.
Yeah.
Okay, because the value is distributed uniformly in 0, 1. And Bob will choose the action 0 with probability 2/3. And the expected value of the winner here, of Bob, is 2/3 plus 0 over 2. So it's a third. So we have 1/3 times 2/3 times 1/3. And if we do the same calculation for every entry, we get this expected welfare. So this is a bit surprising because for the case with unbounded communication, when the players can have an infinite number of possible actions, we achieved 2/3. And this shows that the welfare loss is a bit mild. Yeah? You have a question?
Including the possibility that the players in the auction can randomize the strategy?
Pardon?
Is this including the possibility that the players in the auction can randomize the strategy?
Yeah. It can be shown that the best, without loss of generality, we can think about deterministic strategies both for the players and for the auctioneer. Okay, so I repeat that this is the best solution for the information theoretic problem that we have. This is the best welfare we can achieve by a two-action mechanism. But as I said, we wanted more. We want to implement this solution with dominant strategies. And luckily we can. We can do it, yeah.
So optimal expected welfare is even if like you give some algorithm all the data and it's supposed to pick the allocation? Or what is optimal with respect to what?
This is the best allocation scheme that you can. It's the best thing you can do over all the two-action mechanism with two-action strategies of the players. There is no other combination of strategies of the players and allocation of the mechanism that would achieve a better result.
Because otherwise I would just sit on it.
So, as I said, we are lucky to be able to put prices in this mechanism. So these optimal strategies are dominant strategies. Just to have a look why these strategies are optimal, are dominant, take a look at Alice's strategy. Okay, as I said, strategy is dominant if for any action of the other players, then every action is optimal for Alice. So let's take a look. When Bob bids 1, sends the message 1, then Alice will lose and pay nothing. So she's indifferent between all the actions. But when Bob bids 0, then Alice will win the item only when she bids 1, only when she chooses the action 1. But then she will pay 1/3. So it will be good for her to bid 1 only if her value is greater than 1/3. So this is this shows that this strategy for Alice is a dominant strategy. So let's see some key properties of this mechanism. First one is that we were able to implement the best solution, the best information theoretic solution with dominant strategy. The first property is that this mechanism is asymmetric. Although the players are symmetric a priori, this mechanism is asymmetric, and if we insisted on having a symmetric mechanism, we would have gained worse efficiency, worse expected welfare. And the last thing I want to mention.
And are you claiming that that's a general result, that in
Yeah.
more than two-player games and stuff, that asymmetry is also?
I will show it here for two-player games.
I mean, obviously, it's enough of an example.
Yeah,
But I'm just wondering if you
this
see
is a
that
general.
pattern in
Yeah,
other-
yeah, yeah. This is a general result. Well, the last thing I want to tell is about this threshold. I want to mention that they hold some connection between the threshold, what we call mutually centered. For example, the threshold 1/3 of Alice is the expected value of Bob given that Bob beats 0. That is, given that the value of Bob is between 0 and 2/3. This is 0 plus 2/3 over 2. And the threshold of Bob is the expected value of Alice given that Alice beats 1. That is, this is expected value of Alice between 1/3 and 2/3. And we will see that this generalizes in the general case.
What about the revenue?
The revenue. Actually, we have a full solution also for the revenue maximization, but I won't have time to discuss it here. We were able to reduce the revenue maximization problem to a welfare maximization problem by a trick from mechanism design literature in economics. So we do have, we know what are the best mechanism, or the revenue maximizing mechanism, but I won't have time. Pardon?
That's a different.
It's a different one, yeah. It's not the same one. Okay. So one conclusion that we have is that, a bit surprisingly, the welfare loss from reducing the communication size from an infinite number to only a single bit is quite mild. It's 1/54. Yeah, and that's nice, but this result is a bit misleading because with no communication at all, by just randomize or just giving always to Alice the item, we could have achieved 1/2. So the interesting range is between 1/2 and 2/3, but it's still a nice result. Okay, so now I'll generalize this result in a few levels. The first result here is about, we're still talking about 2 players, but now for any pair of distribution functions, we know that this is the optimal mechanism. So what is the optimal mechanism? It is very simple. The bidder with the highest bid wins, but the ties here on the diagonal are always broken in favor of one of the players. Here it is in favor of Bob. Okay? And we also need one more restriction. We need the payments, these thresholds inside this matrix, to be mutually centered. And again, we can define this notion of mutually centered to be that the first threshold of Alice is the expected value of Bob between 0 and his first threshold. And the first threshold of Bob is the expected value of Alice in this range, etc. Okay.
So now you're going to tell us how that 1/54 scales in this case or not?
Yeah, I think we'll tell you. I won't get into the proof of these things, but I have the expression. This expression is actually a lower bound for the next slide, so I will tell it. Okay, so this is the optimal mechanism for the case of 2 players. But now, once we have the optimal mechanism, we would like to know what is the loss in welfare from this discretization of the action space. So we also have a theorem that says that for any number of bidders, not only for 2 bidders, and for all distribution functions, the welfare loss is at most proportional to 1/k squared, where k is the number of possible bids. Yes? The constant, it's not dependent on it does not depend on the distribution, but it depends on the number of players. I think it's even exponential in the number of players, but we assume that the number of players is constant. Okay. So the question is this upper bound tight? And the answer that it is tight, because from the uniform distribution, we can see that the optimal loss is exactly this expression, which is exactly proportional to 1/k squared. And if you put k equals 2 here, you get 1/54.
Wait.
Okay.
Is this tightness example with 2 players or 4 general?
This is
in the box. That one.
in the box is for 2 players, but we have we have this lower bound also for any number of players.
But probably there will be some.
Well, and the 6 and stuff depends on the number of
Yeah,
players.
yeah. Yeah.
But not on the, but not on the
But-
distribution, because Henry was asking, does the O depend on the distribution?
Yeah, in the upper bound it does not depend on the distribution. In the lower bound, I don't remember actually. Okay, but the upper bound does not depend on the distribution. Okay. So now I want to give another generalization of this model. Actually, we can view this auction model as a specific. Yeah.
The mechanism needs to know the distribution.
Yeah. Yeah.
Okay, so per distribution you can get a loss of order of 1 over k², but you have to know what the distribution.
Yeah, we show that if you want to design a mechanism that will be robust for any distribution, then this is very easy, and this is you can't achieve. The best you can achieve is order of 1 over k. And this is very simple mechanism. So it's not there's nothing clever that we can do for any distribution function without knowing the distribution functions. So now I want to stretch that this auction mechanism is actually a specific case of mechanism design. Note that here in auctions we have 2 alternatives. Either one player wins, Alice wins, or Bob wins. And for every alternative, we attach some social value function. In this case, when A wins, the value for the society is the value of Alice. And when Bob wins, the value for the society is the value of Bob. And the social designer, the social planner, just chooses the alternative such that it maximizes these functions. And we would also like to implement other kind of functions. We would like to do the same for general social choice functions. And here is a theorem that we have. We know that for any multilinear social choice function, I will tell what is multilinear in a minute, then it is true that we have the same phenomenon we had in the auction. The information theoretically optimal solution is dominant strategy equilibrium. There is no additional cost for having dominant strategy equilibrium. And the optimal loss is an order of 1 over k². Okay. So what are multilinear social choice functions? These are functions that actually multilinear functions are polynomials where the degree of each variable in each monomial is either 0 or 1. So we know that whenever the social choice function is looking like this, and in the next slides I will show examples for cases where it is reasonable, then we know these results and more results. Okay.
What's the difference between max and argmax?
Argmax, we want to, the social choice function chooses an alternative. It doesn't choose the value. Okay. For example, in auctions, we want to decide who gets the item and not to find the highest value. Okay. So let's see one example for multilinear environments. Well, this example is of routing in faulty networks. Assume that we have a message to deliver, and we have 2 possible networks to deliver the message through. One of them has a known probability, a success probability of 90%. And the second one is composed of 2 parallel links, where the links are the players, and the players hold some private data. And the success probability in this network is 1 minus the probability that none of these links will deliver the message. So we would like to send our message through one of these networks. We would like to maximize the probability, the success probability. If this expression is higher, we would like to send the message through this network and vice versa. So it is easy to see that for every directed acyclic graph, this success probability of transferring the message from one vertex to another vertex is multilinear in the success probabilities of the links. So we can apply our general results and show that they hold, namely that we can implement the best solution with dominant strategies, and that we can construct mechanism. We know how to construct mechanism that achieve a loss of order of 1 over k squared. So this is the first example. The second example is from economics. This is a well-studied model in economics called the signaling game. This is due to Spence, and this is one of the reasons that he won his Nobel Prize in economics. This model tried to model the job market. We have workers that have different productivity levels, different skills, and they signal their abilities, their talent to the employers, to the firms, using education level, by acquiring a different education level. So there are two assumptions here. The first one is that if I'm more talented, it would be easier for me to acquire, for example, a master's degree. Okay, so this is the first assumption. The other assumption is maybe more problematic. It says that the education itself does not improve one worker's skill or productivity level. So,
What does it say?
that the education itself does not improve your productivity. So it's just a signal for the firm, but it doesn't improve your
I see,
productivity.
but I remain from the time I'm in kindergarten until the time I'm in graduate school, I don't become any more productive.
Yeah. I think they can overcome this assumption, but
I
we
think
will
it's a
take.
bad assumption because you kill your brain cells by studying.
Yeah. So in this model, again, we have a continuum of productivity levels of the bidders. But it is very reasonable that in this signaling game, there will not be a continuum of education level, but only undergraduate, high school, or PhD, and that's all. We will not have too many education levels. And indeed, we can use our general results to show that using k education level, the loss will be at most proportional to 1 over k squared. And this is for multilinear decisions. For example, if the firm want to hire the best candidate, or if it want to hire a group of candidates that the sum of their productivity levels is greater than some threshold, for example, all these decision functions are multilinear, so we can apply our general results. So,
Can you modify the model so that getting a PhD from University X is that still a multilinear function if I say that PhD from University X is better than a PhD from University Y?
Sure.
Yeah,
It's
that's
the same
that.
thing.
Yeah.
You just don't
Yeah.
call it PhD.
I just don't call it, right, so I
yeah,
have
it's
different.
different
right.
education.
But it's still multilinear, so it applies a little.
Yeah,
bit
it depends what the firm wants to do. If
Right, but multilinear is rich enough to certainly to take that into account.
I mean, if you
Yeah,
just
in
assume,
most
okay,
cases.
it's
Yeah,
double
yeah.
as hard to get a PhD from Harvard than from Princeton, you just count them different fields.
yeah.
You're increasing K when you do that.
Yes, you are. You were increasing K.
Okay, so this concludes the first part of this talk. Now we'll go to the second part of the talk, where I discuss the power of ascending price auctions, and I will focus on combinatorial auctions. So what are combinatorial auctions? In combinatorial auction, we have some set of items. Some set of items that we want to sell, and we don't want to sell them separately, each item separately, because then we ignore a very important properties of these or relations of these items. For example, the items may be complements. I would be willing to pay more for a TV and a DVD together than I would like to pay for these objects alone. And they also have the opposite effect of substitutes, where if I have two TVs from different companies, then it will worth to me much less than if I get two TVs alone, than the sum of the values for the TVs alone. So if we allow the bidders to bid for combinations of items, then we can improve the performance of the system significantly. So it turns out that combinatorial auction is a good abstraction for many resource allocation problems. Maybe the most well-known is the Spectrum Auctions done by the FCC in the US, where they want to sell frequencies for cellular phone over all the nation, and it is very complex. I will talk about it in a few slides. But other good examples are auctions or resource allocation for tractors transportations and for airport slots. In these cases, actually, people solve the problem of combinatorial auctions in a different way. This is real world problems. So what is the computational problem in combinatorial auctions? Actually, we would like, again, to maximize the social welfare. We would like to make everybody as happy as we can. Actually, this is also the objective function of the FCC in the Spectrum Auction. There's some law, federal law in the US that says that the designer of the FCC auctions should plan to maximize this social welfare. So what is the social welfare? We want to partition the items among the players such that the sum of the values is maximized. And this is, in computer science, is actually a setbacking problem. So combinatorial auctions have many hardness issues, many economic hardness issues, but I would like to tell something about the computational hardness of this problem. Well, first, it is well known that finding the optimal location is NP-hard, even for very simple cases where each player is only willing to buy, for example, one bundle. Even then, it is very hard to solve, and even NP-hard to approximate within a good factor. Yes?
Does this mean the federal law forces the FCC to solve an NP-hard problem with a large number of variables? They know that the solution is not good either from the computational perspective and both from the economic perspective. Actually, you cannot expect the companies to report the true data, so you won't be finding the optimal solution even if you solve it completely.
But I thought the point, about like FCC versus, like the search term kind of auctions, the AdWord kind of auctions, is that the FCC auctions are for such expensive things, and it is a relatively small number of participants that even though it's NP-hard in the number of participants, they actually can find the optimal solution. If people were telling their true valuations, you could actually find the optimal or not.
Yeah, I agree that
it's a
the number of
relatively
participants, but if we take a look at the second computational problem, the one of the communication, then even if one bidder wants to transmit his value, he has to transmit a number for any subset of the items. Okay? For any subset of the states in the US, I have to put my number. So the input for the algorithm has an exponential size. So even if we have very small number of participants, we still have computational issues.
So it's exponential it's 2 to the 52 times the number of frequencies.
Yeah, I don't know if they sell states or counties inside the states. I don't know exactly how they divide the US. But I agree that the most important issue, that, at least from my point of view, is this communication barrier. And this will be the focus of this work.
Right, because the optimal, without that, I don't.
Yeah.
You're talking about things which are hundreds of millions of dollars, and without that exponential burden, I think.
Yeah, in the FCC, I think that the data is, the number of participants is relatively small.
Well, I have actually a question with this NP-hard.
Yeah.
Given that your input is sort of exponential in N, you say it's still NP-hard in the input size?
Even if the input size is, even if...
talk about the same representation, or is it NP-hard even if you take account the whole?
Even if each player has only one secret number, if he wants only one bundle, then it is still NP-hard even to approximate. Okay. In the number of items and in the number of items, actually. So in this talk, we will focus on the issue of communication.
So as usual in these cases where we have an exponential input to the algorithm, we use the oracle model. The auctioneer will query the participants by using a set of queries that he is allowed to ask. And then he will gather the answers, and he will think about it and come out with an allocation. Okay, so this is our oracle model. So the question is, which kind of queries should we allow him, this auctioneer, to ask? And the most commonly used, and maybe it seems to be the most powerful query, is the demand query. And the demand query is actually very simple. This is the query that every one of us faces when he goes to the supermarket. We see prices for the items in the supermarket, and we decide which bundle of item we want to buy. Okay? So in the demand query, we have a price for each item, and the player decides what is his favorite bundle of items under these prices. Or formally, we have prices per each item, and the player should report the bundle that maximizes his value for the bundle minus the sum of prices of the items in this bundle. Okay? So this is the demand.
Does he have a budget or not?
He doesn't have any budget. He's Bill Gates. So it turns out that in most cases, in most combinatorial auctions that are being performed in the real world and in the literature, most of them use this the following scenario. They start with a very low prices, for example, from 0 prices, and then the bidders are queried with demand query. They answer this demand query, and the prices start to go up. Okay, and until the auctioneer stops from some reason. So this is the definition of ascending auction. This is a series of demand queries in which the prices can only go up in time.
So why should the bidders answer these?
I will get to it in a moment. Actually, we don't deal this. We don't treat this question in this talk, but I will tell why in a minute. So let's talk a bit about the Fcc Spectrum Auction. This is data taken from their website. So the auctions in the FCC are currently done by an ascending auction. Okay? They use this demand query and they increase the prices. And there is a great debate among the economists and even the computer scientists on what is the best way to perform this auction. And there are many suggestions for different auctions. But it is interesting to see that all of the suggestions are ascending auctions. None of them use another way of communication. All of them use ascending prices. And the debate is about the way to use prices per items or prices per bundles or etc. But everyone is proposing to use ascending auctions. So this is a very common tool, and it is very interesting to know what are the boundaries of what we can achieve, what may be achieved using this tool of ascending auctions.
Are these public? In other words, do I know who still bids with me?
Pardon?
Are they private bids or are they public?
They're public bids, as far as I know. Okay, so we see that there are a lot of work in the literature about auctions. Most of the auctions are ascending auctions. Some of them use item prices, some of them use anonymous prices. I will not get to it now. But in this work, we try to systematically analyze what is the power of each family of auctions in order to know what can be achieved and what cannot be achieved by each family of auctions.
And you'll tell us how you quantify power.
Yeah, I will tell you.
So nobody does sort of what the Seattle fish market does, where the fisher says $10, $9, $8, I take it.
Descending,
auction.
yeah. Actually, we treat descending auction in this work, but I will not talk about it. This is very similar, okay?
As long as it's monotone.
As long as it is monotone, yeah. You can show. Actually, we propose some hardness results, and all of them also hold for descending auctions. So the main questions that we would like to ask is, can the optimal allocation always be determined by an ascending auction? Okay. This was unknown. Many people suggested their mechanisms and said that using many experiments, they suspect that this is efficient, economically efficient, that it achieved the optimal solution. But we would like to know, is this true? And we have two strong assumptions. The first assumption is that the bidders will answer truthfully to the queries. And the second assumption that all the participants will not have any computational restrictions. Okay? But since we will present hardness result, then these strong assumptions will only make our results stronger, because we show that even if we can make the bidders answer truthfully, and even if all the participants can solve any NP-hard problem that there is, even then, ascending auction cannot elicit enough information in order to find the optimal location. Okay, so this is what we will do. And the first result that I want to show is a negative answer. This is a theorem with a very simple proof. I will show you the proof. It says that no ascending auction that uses item prices can always find the optimal location. We cannot be guaranteed to find the optimal location with any ascending auction. Okay, so let me sketch the proof. We will only need 2 players and 2 items for this proof. Assume that Bob is willing to pay $2 for an apple, $2 for a banana, and $2 for the combination, for the whole bundle. And Alice is also willing to pay $2 for the whole bundle, but she has some unknown values between 0 and 1 for each one of the items. And now, let's ask ourselves, what is the optimal allocation in this case? So the only way to achieve more than expected welfare of 2 is by allocating one item, one singleton to Alice, and the second singleton to Bob, or vice versa. Okay? Recall that we cannot allocate an item more than once. Okay? So these are the candidates for the optimal. Allocation. So actually, the optimal allocation depends on the question which one of these values is greater. And what we claim is that using a single ascending trajectory of prices, we cannot know the answer. We cannot know which one of these items is greater. And what is the main idea here? Well, think of this auction. It starts from 0 prices. What happens with the 0 prices? Then Alice will clearly demand this whole bundle because it gains her a payoff of 2, while every singleton gains her at most 1. And now we will start increasing the prices. So we claim that as long as both prices are below 1, then Alice will still demand this whole bundle. Or in other words, as long as both prices are below 1, we will not have any information about these secret values. And why it is true, it is easy to see this sketch. Alice, the payoff for Alice is this difference between 1 and the price of an apple, and this difference between 1 and the price of a banana, and this is clearly greater than the difference between this value, which is at most 1, and the price of a banana, and this value. Okay, so we claim that as long as both prices are below 1, we will not have any information about these secret values. So what the auctioneer has to do, he has to arbitrarily choose some item and increase its price to be greater than 1. But then, clearly, Alice will not demand this item anymore. So we will not have any information about one of the items, so we will not be able to know which one is greater. So this is the first hardness result that I'll show. So we know that ascending auction cannot find the optimal solution.
But
But
the problem is sort of that Alice will never want a single item, right?
she will never want.
Depends what he charges.
She's not
Yeah.
the only person in the system. You have to
Right.
input other persons want when you want to work.
Yeah, competition.
Everyone refers to.
Well,
Yeah.
because as a combination that is worth more, a lot more than any single item put together.
Yeah.
If we do transportation networks, ship something from one place, that two networks allow it, one doesn't.
Okay, thanks. So we saw that an ascending auction cannot find the optimal location, but maybe we can be close. Maybe we can approximate the optimal solution. And the next question is really, can we find good approximation using ascending auction?
Wasn't the point really that no matter what's the price, Alice always wants both items?
No, if one price is very high, like infinity, she will ask for the other singleton.
Always.
So again, we have a negative result, which was quite surprising to some of the economists, that actually no ascending auction can guarantee more than approximation of square root of the number of items.
Single ascending, that's very
Yeah.
important. Right, if you tested it once and the other, and then you would,
Yeah,
then you would discover. Yeah.
if you have different ascending auction per each player with item prices, this result is still true. The only way you can avoid this result is by using a different ascending trajectory for each player with bundle prices, with exponential number of prices, price per each bundle.
Right, and I
Or
guess that would
subset.
really piss off the customer, like when Amazon tried
Yeah.
charging people different prices, Amazon tried
Yeah.
this at one point, they tried charging different people different prices for the same book at the same time.
Yeah, and they don't like it.
And
Yeah.
when customers realized that, there were absolutely, to get information.
Yeah, I agree.
Right.
No, you
And-
think
customers
does not
went nuts.
exclude that I could test try prices by, just like the supermarket does, by having one item on sale tomorrow and sort of going separate, single ones up and down.
Yeah, we are limited to this framework of ascending auction. In general, we show in this result that it is not a problem to acquire all the data using even demand queries. It is not a problem, but if you are restricted to ascending auction, you cannot do it. Yes?
Are you knowing a very serious constant factor? Because in the previous example, you can get within 6% of the optimum by just allocating random.
Yeah, actually, I will in the next slide I will sketch the idea behind the proof of the approximation result. Okay, so let me just say something more about this result. We see that a single ascending trajectory of prices cannot elicit enough information in order to have a square root of approximation, a square root of the number of item approximation. And it also holds even if we use bundle prices. Even if you use an exponential number of prices, a price per each bundle, even then we cannot achieve better approximations than the square root of the number of items. And as I said, there were several suggested auctions that used these bundle prices with a single trajectory that claimed that they work efficiently, economically efficiently.
Claimed, meaning
They
just thought
did
they-
experiments.
Okay.
Experiments.
So this is the worst case.
This is the worst case.
You
Yeah.
have some assumption about the distribution.
No, we don't have. This is the pure worst case. Yeah. So the answer from the economist may be that this is not realistic because in reality we have very strict distributions on the valuation. But this is a worst case analysis. Yeah. So what is the idea behind the proof? Well, in order to prove this theorem, we have to build some combinatorial design. We have to we assume that there are n players and n squared items, and we want to create the following design. We want to create a partition of the items per each player,
and we want every two bundles from different partition to intersect. Okay? For example, let's see what happens here. We have 3 players and 9 items, and indeed we can see that every 2 bundles from different partitions intersect with exactly 1 item. Okay, and we can we have an explicit.
Just once more, what is your intersection?
Intersection. Take this bundle, this red bundle,
Oh,
and this red bundle. They have this item in common. Okay, and it is true for every 2 bundles from different partitions.
So you say the things of light color are in the same bundle?
Yeah. Thank you. So we have an explicit construction like this example. We use the properties of linear functions over finite fields to. You can see that actually these are linear functions, these bundles. And the main idea again is like the previous proof that I showed you, is that the optimal solution is some partition, but in order to gain any information about this, the value of this partition, we must increase some prices. And when we increase the prices, we hide the information that we will not be able to recover. So this is the idea behind the proof. So what further research can be done on such things? First, we may justify the design of hybrid mechanisms. For example, we show that auctions that use item prices have some strengths, and auctions that have bundle prices have some strengths, so maybe we can combine them and get the strength from each one of them. And we can also identify other useful patterns. For example, in work I did with Moshe Babayov, we designed auctions where the bids are for geometric areas. For example, in the FCC auctions or in the Google AdWords, that you can specify in which geographical area you want to bid for. So this is one another communication pattern that we can identify. And the final issue is to identify distributed communication patterns and try to analyze them. So to summarize, in this talk I'll try to study some, to show you, to survey some, the power and limitations of some communication patterns. And we saw that these communication patterns, by only looking at this communication pattern, we can tell a lot about the power of the mechanism, of the game. And we have 2 different different conclusions. The first one is that even if we have very low communication level, we can still have nearly optimal results. And the second conclusion is then some very popular communication patterns, like ascending auction, may have a worst case, very poor worst case performance. So thank you very much for your attention.
So if we look at your previous result, where guaranteed sort of 1 minus O of 1 over k squared,
Yeah.
can you apply that to the FCC spectrum auction? What would that mean? What would you communicate?
Actually, we have hardness results. We don't have matching upper bounds, but we can apply the hardness result.
But the hardness is sort of for ascending auctions. It doesn't say that any communication pattern doesn't work. So maybe there would be some pattern where these guys, some protocol where the guys have to tell me something totally different and not the prices.
Yeah, there are other works that show that, for example, with the communication, polynomial communication, you cannot do better than, again, a square root of m approximation. So there do exist other results that.
So the problem is that your positive results don't apply to combinatorial auctions.
I didn't show here. We have positive results, but I didn't show them here. So.
No, but your original, you showed us first.
The first one is only for a single item, yeah. You can't apply it for auctions. Yeah, unfortunately.
think a lot of you are meeting with Liad, and you're just here for the one day, right?
Yeah, actually I leave tomorrow afternoon, but
Okay, so if there's somebody who's not on the loop who really wants to talk to you, try to arrange something. He's
Okay,
probably going
thank
to
you.
get out relatively early since he just got in from Israel on Tuesday. So be nice to him in the later interviews.
thank you.